Hey folks, part two here talking about properties of light and absorption of light, and we're now going to focus on Beer's law. So the format or the form of Beer's law is actually quite simple. And it tells us that absorbance is equal to epsilon times B times C. So let's look at what all these are. This also helps us understand why absorbance is a nicer quantity than transmission, because it is linearly dependent on the concentration of the absorbing species, the path length, that is, the distance that the light passes through the sample, and in a property inherent to the species or the molecule itself that's called absorptivity. And if path length is given in centimeters, like let's say you're actually doing an experiment, the standard is that you have your sample in a cuvette that is a 1 centimeter path length, and so this is just equal to 1, so it simplifies everything out. If concentration is given in molarity, then the absorptivity would be per centimeter per molar, because absorbance is unitless. Okay, so this is the all-important equation, and absorptivity will depend on, again, the species and the temperature that you're at. And those are the kinds of things that you would look up in a table. So here's figure 18.6 from our textbook, and it shows the absorption spectrum of potassium permanganate at 4 different concentrations. So we have an inset as the 4th, and then we have 3 here. And so we see major absorbances of like upwards of 6 and 7 almost when it's in the millimolar range concentration. The concentration is reduced down to the hundreds of micromolar, and the absorption spectrum actually looks exactly the same, just shrunk down. Right? It's like shifted by a multiplicative factor. And then another 10 times lower concentration, and the absorbance goes down by a factor of 10, but it still has the same shape. And when we zoom in, even another 100 times smaller, it looks like the same shape that we see here. And so we see that the absorbance and the absorption spectrum are linearly dependent on concentration. So then we can plot absorbance against molarity, and even over 4 orders of magnitude, or a factor of 10,000, it is still linear. So there are all sorts of useful implications and practical applications of this fact that we have a linear dependence on concentration. And so anytime you have an equation like this, right, imagine rearranging it, and you can solve for anything. So let's say you have a situation here, back here like this, where we have a known absorbance and a known molarity. And we also know that we have this relationship, right? And so what we've essentially just created here is a standard curve, or a calibration curve, right? So any other sample that you might have of this, like say an unknown concentration, we can take a spectrum, right, do spectrophotometry of it, look at the peak absorbance at 555 nanometers, and get the absorbance value. Epsilon would be known from the standard curve. We know the path length, and thus we can find unknown concentrations. Quite straightforwardly. Okay, so here's a nice example. This is from the textbook, of how you might have a problem like this. So let's say we have gaseous ozone, and we have a known molar absorptivity, right, from past experiments, 2,700 per molar per centimeter at the absorption peak near 260 nanometers in the spectrum. So we can find the concentration of ozone in air if a sample has an absorbance of 0.23 in a 10 centimeter cell. And importantly, air has a negligible absorbance at this wavelength. So that all of the absorbance is due to ozone. Okay, so we start with Beer's law, and we're solving for concentration. And we have all of these terms, right? 0.23, unitless. We have 2,700 per centimeter per molar times 10 centimeters. So the centimeters will cancel out. We have 1 over per molar, that's molar, and we just get 8.5 times 10 to the negative 6 molar. Okay, so there's all sorts of ways you can apply this, and it's very, very useful. But Beer's law, even though we saw it over a huge range in that past example, linear with regard to concentration, there are some limitations to its ability to still give us reliable answers. So you can find a list of these in a section in page 394, but basically deviations from Beer's law can occur if your light is not monochromatic, right? And if measurements are not being made at the absorption peak. So you always want to make sure that you have monochromatic light and that you're looking at the highest peak on your spectrum. It can also deviate if the analyte or other solute concentration is too high, right? The difference in you basically you can saturate the absorbance where you no longer can tell differences very much. The same as if it's too low, right? If the sample concentration is too low, then you might not see absorbance much over the noise. If the analyte participates in a concentration-dependent chemical equilibrium, that can impact how light passes through the sample, and if too much stray light reaches the detector, or if the sample temperature changes. These are all limitations of Beer's law. Okay, so in lab this week, we're going to be using spectrophotometry to analyze a mixture. And so we're going to create a calibration curve based on peak on the spectrum of actually, it's going to be caffeine and benzoic acid in a sample of soda, right? Like Mountain Dew or something like that. And then using our calibration curve, we'll take the actual soda and figure out how much caffeine is in it. So in a similar fashion, I want to walk through basically that entire process with an example. And this is starting on page 400 in your textbook, but we'll walk through it here together. So we're going to be looking at measuring nitrate. Okay, so we have a sample with an unknown amount of nitrite, and we want to use spectrophotometry to determine what that concentration is. So we're going to create a standard curve or a calibration curve, right? And how should we do this? Well, here is the spectrum of a standard nitrate solution with a known amount of nitrate. So this is a very basic, simple peak, but we want to identify what we would call lambda max, which is the maximum absorbance. And that's actually, lambda is wavelength, right? So we could identify here that the maximum absorbance occurs at 543 nanometers. So then what we would do is set our spectrophotometer to look at just 543 nanometers and give us the absorbance value, right? We know that if we had a lower concentration, we would have a peak that looked like this. If we had a higher concentration, right, we'd have a peak that would look like this. And so the absorbance at lambda max tells us the concentration because, of course, we have this equation. And in all of our cases here, epsilon and B will be constant, right? We're going to set up a situation where we have the same kind of cuvette. It's the same species that we're looking at, so epsilon stays the same. And so if A changes, it has to be because of concentration. So we can set up or design an experiment that helps us collect data like this. So we would first take a blank, right, which would be all of the solvents and all like the standard cuvette and everything, but without any of the sample. So then, as we've talked about before, that means when we do put our sample in, if all the other stuff is the same, at least at 0.003 absorption units must be subtracted away because that's not actually the sample, it's just all the other stuff. So we need a blank to subtract away. But again, we're looking at 543 nanometers specifically at that lambda max. So if we have three standards and we determine the exact absorbance there and then subtract away from the blank, then we can use any 3 points to make a line, right? And absorbance is linear with respect to concentration, so it should be a line. Y equals mx plus b is our equation for a line, right? And then we can plug this into Excel or something and produce a linear regression and get a line. So here, the slope is 0.1796, and the y-intercept is 0.0015. It's up to you, and it's kind of, there's no right answer necessarily about the y-intercept. It should theoretically be zero, right? So zero concentration, there should be zero absorbance. Now, when you're doing like a linear regression or like a line fit, you can force the y-intercept to be zero, or you can leave it as a variable. And I don't have the right answer on what to do there. So it's kind of a case by case, and I'd be happy to talk more about it But I guess maybe the standard is to leave it, let it float, and see what you get. See how good of a line fit it is. Set it to 0, and then see how good of a line fit it is. So, right, once we have this line, we have an equation, and there's two unknowns, right? There's the concentration, and there's the absorbance. So using this actual example, right, we're going to find the concentration. We would take the absorbance, which has been corrected, baseline corrected, or blank corrected already, minus the y-intercept divided by the slope, right? So if we go back to our data, we have two unknowns. Let's say one of them, the absorbance, is 0.278, right? So if we come in here, we put 0.278, then this would equal 1.56, which we see right here on the plot, right? But we can also just do it from our table or from our analysis, right? And so we have two samples here, right? So we do both of those and see what we get. So this is basically what we're going to do in lab, right? We're going to have standard caffeine samples with known concentrations. We'll determine the lambda max, like where do we want to look. We will have a plot like this where we take the known concentration, we determine the absorbance, and we will do a line fit, and then we'll take our soda sample, determine the absorbance at that peak, and analyze how much caffeine is in it. We'll also see if that fits what's on the label. Okay, so there are a lot more sample problems that we could do, but I think we'll do those together if you want, and you can definitely practice some on your own. So I'm going to end this here, and when we meet again, we'll go over anything we want to. We'll do some sample problems and go from there. So there is a chapter 18 homework, and really that will provide most of the practice problems that you're going to need. So get looking at that, and let me know if you have any questions, and I'll see you next time.